Cool. Thanks, Peter, for the introduction. Today we're going to talk about this paper that's sort of been making rounds online. There's a lot of noise about it for the past month. It's not been peer reviewed as far as I know, but it is under review, as the authors claim. It's by authors from MIT, Caltech, and Northeastern universities. And as Peter alluded to, it is a paper that proposes an alternative to MLPs, so multi-layer perceptrons. And it does so kind of in an interesting way. So maybe to start, they propose this idea of Kolmogorov-Arnold networks, and they're based on this theorem called Kolmogorov-Arnold representation. So to directly sort of contrast that with the universal approximation theorem for MLPs. So maybe I'll introduce both of these things. So the universal approximation theorem for MLPs states that any sort of continuous function can be approximated by I think one hidden layer deep MLP that with some arbitrary with a fixed number of neurons and assuming access to infinite data or enough data to approximate. So it's basically trying to say that the MLP is able to approximate sort of any function. I might be a little bit off on the details on that, but that's roughly the idea. And the difference between the Kolmogorov-Arnold representation is that this Kolmogorov-Arnold representation says that any continuous function can be represented or approximated by any continuous function that is multivariate can be approximated by a series of sums of univariate functions. So what they're trying to say is that, yeah, given any multivariate function, we can approximate it with multiple univariate functions. And in terms of the larger architecture of the model, in an MLP, we've got nodes or neurons and the connections and the weights between them. And in MLPs, we aim to learn or train the weights, whereas the activation functions are on the neurons. In contrast with CANs, neurons have very simple sum operations. However, the edges themselves have activation functions. So they kind of flip it around a bit. Yeah, so there is so these functions are nonlinear as well on the nodes, whereas the activation functions, so these functions are the activation functions are on the edges rather than the nodes. Okay, so what is the I guess the interesting thing about this is that they haven't really proposed a problem that they're trying to solve. It's the same MLPs are quite heavy in terms of parameters for transformers, but they're not very interpretable. But I don't think this is like a very large problem to solve, or has been solved via other means. I think this is it's a paper that describes an alternative and also explores this idea quite in depth to kind of propose various improvements in both interpretability of neural networks and approximation theory as well. So yeah, the CANs are inspired by the Kolmogorov-Arnold representation theorem. They replace each of the weights parameters by a learnable 1D function. And each of these 1D functions is parameterized by a spline, or more specifically by a B-spline. So as I mentioned before, the nodes, they simply sum the incoming signals from these 1D functions without really applying any non-linearities as that would happen in MLPs. I guess the immediate thing about this is that, okay, we're now replacing every parameter with an activation function. Like, wouldn't this make this network horribly expensive to run? Yes. However, what they found is that they actually allow much smaller computation graphs than MLPs. So for partial differential equations, they found like CANs are 100 times more parameter efficient than MLPs. So that's how they justify the fact that they can add activation function, replace weights with activation functions. So it's interesting because this Kolmogorov-Arnold representation theorem, it used to be like people tried using it for AI and for deep learning, or I guess at that point machine learning. However, they found that they kind of got stuck at this this shape of the network with a maximum of 2 layers and the width being 2n plus 1, with n being the input size of the network, and that was the case until this CAN paper, where they propose a way to generalize this representation to any arbitrary widths and depths, which allows you to build more complex networks and potentially represent more complex functions. However, they kind of claim, not claim, but they also note that the CANs are nothing more than combinations of splines and MLPs. So if you look at these functions here, or rather these graphs here, you can see that the structure of the network is very similar to like an MLP or feed-forward neural network. So the overall structure is similar. However, the splines kind of appear within individual edges, as the activation functions are represented as B-splines. So, okay, so one of the problems that they found was that when you try to approximate a function using splines, there's a serious cursive dimensionality problem. So cursive dimensionality being this like basically there's issues with if the larger the input size in terms of its dimension, the more problems are there down the line with like approximation, comparisons, calculating distances between points in the space. So that is a problem within machine learning in general, and they found that this is also a problem with splines.
The other big difficulty in terms of the cursor dimensionality is that you need a lot more data to fit the model, just because the space is, yeah.
Because the space is so large, so there's a lot more sparsity within the space.
Yeah.
We need this.
Yeah. So okay. So what does this say? Yes. So the interesting thing about what they propose is that they leverage this Kolmogorov-Arnold representation as the internal degree of freedom within the network. So you could think of it that way, where the representation, or rather the things that the network is trying to learn, can be learned by sort of manipulating the external degrees of freedom in MLPs. So we can construct networks with varying number of layers, with varying widths of each layer, and that's the external degree of freedom. However, MLPs cannot easily focus on any specific neuron. Like the modification during training happens across the network, whereas in CANs, you've got the ability to do both. So you can both change the network globally by changing the number of layers, the width of those layers, but you can also target individual neurons, or in this case, individual activation functions on the edges, which gives you this internal degree of freedom, and that's quite interesting. So to give this idea that, so maybe let's focus on this function here. So we've got a multivariate function. which has some summation, the sign, and raising to the power of 2. And they're saying that given enough dimensions within this function, splines would fail because of this curse of dimensionality. Whereas MLPs could potentially learn this, but they are very inefficient for approximating the exponential and the sine functions when you use things like ReLU activation functions. Whereas CANs, which is what they are proposing, can learn both the compositional structure and the univariate functions quite well. So that's why they outperform MLPs. It's quite good because they shared code for this paper as well, and it's been quite heavily reused and shared and forked on GitHub, which is cool. Yeah. So
about this example you just gave, I've always this is more of just a comment than anything, but I've always wondered, like, I mean, I'm sure that linear functions are the easiest ones for MLPs to learn, but maybe not because of the ReLU activation. But
yeah,
I've always wondered, like, what functions are really hard for an MLP to learn, and whether we can like increase their expressiveness by adding something in. I'm sure there are people who know the answer to this quite well because I'm sure it's studied, but I've never known that, and it sounds like, I guess, just like exponentiation or sine functions are two things that MLPs really struggle with.
Just trying to see.
Wondering if there is a way that, like, small changes we can make to an MLP to make them better at those things.
Yeah, I guess maybe a different activation function is probably the culprit there. But I'm not sure. It's a good question.
I think it would have to be more than that, because like an MLP, like a sine function is periodic, and I don't even know if you could learn a periodic function easily with. I guess you could.
Yeah.
Could you learn a periodic function easily with an MLP? I'm not sure.
There will be a little bit about that in one of the toy examples later in this paper, where they kind of cover this, how an MLP versus CAN can learn sort of periodic repeatable functions. Yeah, we can have a closer look at that later. Yeah, so more about this Kolmogorov-Arnold representation. So as it states, is that given a function f, which is a multivariate continuous function with some bounded domain, f can be written as a finite composition of continuous functions of a single variable, so univariate functions, and the binary operation of an addition. So if we have this function, we can express it as a sum of these univariate functions. Now, this is a little bit confusing in this, at least for me, it was a little bit confusing, is that this actually represents two CAN layers. So this is the original equation for the Kolmogorov-Arnold theorem. However, what the authors of this paper did was that they almost relaxed this assumption a little bit of this equation, and instead they split it into two. So you can, and that's what allows it to have to be able to stack these layers together. Because this original representation, which is partly why this line of research has been stuck for a while, this allows this kind of stacking behavior from happening. So, is there anything else I wanted to cover about this? Yeah. So this is kind of an interesting point, which is they mentioned that even though we can represent this more complex multivariate function as a series of univariate functions, these 1D functions can be non-smooth and even fractal, so they may not be learnable in practice, which is what sentenced this this Kolmogorov-Arnold representation to, they call it the death in machine learning. Yeah, so looking at, so they're basically saying that we don't need to stick to this original equation, but we can split it into two, which forms two CAN layers. So now they talk about this architecture a bit more. So let's say we have a supervised learning task. We assume that we're done if we can find the appropriate univariate functions that approximate this function f. And we can do that by having some inputs and outputs as a supervised learning task. So this sort of inspired the authors to then start thinking about, okay, can we create a neural network which can explicitly parameterize these univariate functions here? So they also noticed that all of these are univariate functions, which means they can be parameterized as B-splines, so with some learnable coefficients. So I'm going to very briefly mention about B-splines and what they are. So you can think of them as a combination of like n Bezier curves with some control points. So you can think of, let's say this is the CAN layer, or rather the CAN network, and each of these activation functions on the edges is a B-spline. So a B-spline could be it's essentially a combination of these Bezier curves. And what that allows it to do is have a series of control points. And this is what gives the network I guess, this local degree of freedom where you can sort of tweak individual control points via these coefficients here. And that allows you to individually modify the function at specific points, which is a lot more, I guess, gives you more freedom of expression in terms of like compared to MOPs. So they construct those functions out of these B-splines. They also, I'll talk about this a little bit later, but they say that they can increase the granularity of these B-splines. So let's say we start with like a B-spline that is a combination of five Bezier curves. You can extend it to be a more fine-grained B-spline later if you wish so, and they do that within this paper as well. And what that allows you to do is have more of these control points, which means, again, more degrees of freedom on how to modify each individual activation function on these edges. Yeah, so they talk about these learnable coefficients of local B-spline basis functions, and right, yeah. So they say that such a network is too simple to approximate any function arbitrarily in practice with just using these smooth splines. So therefore, they generalize this to be a wider and deeper network. They mentioned that a single Kolmogorov-Arnold representation, as that equation 2.1, corresponds to two CAN layers. So they basically mentioned that within this paper, one of the major contributions is a way to generalize this to multiple, like more layers, and you can stack them together. I can skip over that. Yeah, so they're simply compositions of two CAN layers, so you can stack them together. Yeah. I guess, yeah, we can talk a little bit more about how these sort of neurons combine together. So just to kind of, as I mentioned before, these neurons are simply summations. And there's like an equation which they used that determines how many activation functions will be necessary given a number of inputs and the number of layers. And I think that equation was somewhere here. Yes. So yeah, they mentioned that these are the pre-activations. And then the activation value of some specific neuron is simply the sum of all incoming post-activation. So from that, they can derive how many activation functions they need, given some number of neurons. Yeah. They attempt to rewrite this sort of equation, which is this function composition of multiple CAN layers, as sort of similar to how that Kolmogorov-Arnold theorem is. However, it's a little bit too confusing, I think, which is, yeah, they call it the cumbersome. And they are claiming that their visualizations are more clean and intuitive than that. So, yeah, the important bit is that all of these operations are differentiable, so we can train these with backpropagation. This is not possible for like the simple Kolmogorov-Arnold representation for a single function. Yeah, and these are more of the details about how each of these activation functions is constructed. So we have some basis functions for those B-splines, and each spline is essentially parameterized as a linear combination of B-splines. And yeah, so it's a combination of all of these. And they also add this W factor, which I guess, yeah, you could refer to this as the weight. It could be absorbed within the basis function and the spline function. However, they say they include it to better control the magnitude of the activation function. Yeah, they initialize it similar to how you would initialize MLPs with the Xavier initialization. This one was something that I was thinking about, which was like this update of spline grids. So as I mentioned before, you can update this grid from a coarse-grained grid to a more fine-grained grid. Now, they say that this is dependent on the input activations. And I thought this is a little bit too underexplained because they don't go into detail on how, in what way is it dependent? Like what was the relationship between that? Yeah. Yeah, and they talk about
to clarify, the backpropagation works on the splines itself, right?
yes, it works on the B splines.
Yeah, so it moves the control points around.
Yes, it does. Yeah.
Okay, thank you.
Yeah, so what we are backpropagating over is these coefficients here. So essentially, they modify. I think they modify the control points of each. Yeah, they modify the control points of the B splines. Okay. Now they go into a little bit more detail about like the parameter size of these networks. So they notice that MLPs have lesser number of parameters than CANs. However, CANs usually require much smaller n, so the number of layers than MLPs. It's interesting that they note that actually shallower CANs are better at approximating certain problems than deeper CANs. So, for example, for 1D problems, we have a univariate function. You can have a very small CAN with basically one layer CAN, which is essentially a spline approximation. So for higher dimensions, they go now into detail on how do you sort of generalize this behavior of CANs with higher number of layers and also higher number of dimensions. So they talk about this. They talk about this with this example function, which has four inputs, so 4-dimensional input. And they say that this can be smoothly represented by a CAN of this shape. So we have a 4-neuron layer, then a 2-neuron layer, 1-neuron layer, and 1-neuron layer, which is 3 layers. But I guess this one is how do I talk about this? So yes, so for certain problems like this one, a simple sort of 2-layer CAN may not be able to represent these, and to like facilitate this analysis, they assumed the smoothness of activations, but instead they allowed it, not instead, but they also allow all of the representations to be arbitrarily wide and deep. So yeah, so they talk about this theorem here. So suppose we have this function that admits a representation, where the representation is a function composition of multiple can layers, where each of those can layers is some number of neurons, and each neuron is consisting of this B-spline represented activation, not the neuron, but the weights are represented by these B-spline representations of activation functions. And what they're trying to show here is that there will be some kth order B-spline functions such that we have a bound on sort of the error, or rather the difference between these two representations. So the original function f and also the can representation of that function, such that this is given some constant c that is dependent on f, will be less than combination of that constant with the grid size. So essentially what this, I believe what this means is that we can use this representation, or the can representation, to approximate this function f up to some, I think, order m of derivatives. I think, Peter, would you be able to explain this a little bit better? Because maybe I don't quite know how to put it into words best.
Isn't it just showing that given the network is stable, it doesn't blow up? I had a feeling that this was very much a circular argument, because you know, if you assume that it already has that shape, it's very easy to sort of show that everything is well behaved. But it's, I think, the first step of having it such a well behaved form is, I think, the difficult bit, really.
Yeah, we discussed this a little bit before this presentation. We were wondering the same thing. Like, it's hard to tell whether this is a trivial result or not. But yeah, it's
I think.
What?
I would err on the side of trivial. I think it felt like it, yeah.
Okay, so the only thing I was thinking about, which may make this a little bit of a more tight result, is that you've bounded not only the difference between the functions, but the difference between all of like the errors in terms of the difference, but also in terms of its derivatives as well, which is stronger than if it was just a difference between the two functions, because then you can't have like large jumps between the two functions ever as well.
I guess, yeah, I think they're trying to say that the functions that are going to be that are, or rather these compositions of can layers, are not going to result in sort of staggered functions or staggered representations where it kind of but rather it can smoothly represent that function f. And I think, yeah, as you said, the fact that it's a CM norm up to the sort of order of m, which means, yeah, they're continuously differentiable, and it's a stronger assumption there.
What I've been trying to, I didn't pick up on this when I was reading the paper, but now I'm trying to figure out if, so the f is composed of these large phi layers, and then the network, like the CAN network that they're comparing it to, is composed of these large phi layers with B splines and a specific grid size. But are the
Yeah.
original phi layers composed of these, like an infinite number of B splines or something like that, or are they composed of just like smooth functions? What's
So the phi, the large phi, I think represents a single layer that has multiple activation functions within it.
but
Because remember, they don't talk about, like, the layers in CANs are not the same as layers in MLPs, so we cannot think about them as like neurons.
but my
So they,
my point is that are the functions in 2.14 just any
Mhm.
smooth functions, or are they B splines as well?
no, so each of these contains multiple, like, lowercase phi functions, and each of those lowercase phi functions is composed of a B spline.
But they're saying later on that the one with the G superscript contains B splines. So that's why I was wondering if the ones that in the original
Yeah.
2.14 are just any smooth function.
I think the G is set per layer on a per layer basis.
I'm
Maybe
pretty
not. Yeah.
sorry. I'm pretty sure they are saying that this is any smooth function, and we can approximate it to this accuracy. That's what they're trying to say. I don't know.
Okay, yeah, that makes more
That-
sense to me as a more powerful result.
I'm not sure, because they kind of go into detail of this here. I guess maybe yes. Yeah.
or at least any smooth function that can be expressed with this representation, which is not.
Yeah.
That, I mean, that's the.
I mean, they also talk about the fact that, like, each of these, each uppercase phi is a matrix of 1D functions, opposed to a single function. So I'm not sure whether they treat that as a, like this one here would be a matrix of these lowercase phi functions.
Yeah.
Yeah. So if I go down, so provided that these assumptions that they presented in theorem 2.1, CANs that have a finite grid size can approximate the function well, with a residue rate that is independent of the dimension of the input. And that's kind of what they cover in this proof, which I think that they're trying to say, like, that beats the curse of dimensionality. Next, they talk about the neural scaling laws. So they're essentially saying that the test loss, like, to describe what the neural scaling laws are, in this case, is like the test loss is like proportionally corresponds to, like, the number of parameters to the negative power of alpha, which is the scaling exponent. So the higher the alpha, the lesser the number of parameters that will be required to achieve the same test loss. And they are saying that their approach has the largest and best scaling exponent compared to any other works, which they achieve. They arrives at, like, alpha of 4, which means it's like, if you look at some of these.
Wait, okay. I just thought of something.
Yeah.
Again, I wish I had more of a background in this. I think we all do. It's just hard to have a background in this unless you're do theoretical ML. But okay, they chose B splines, cubic splines, but they could have chose linear splines, and then they would have had alpha of 2. So
Yes.
But you probably think that, like, linear splines aren't very expressive. So I feel like that seems like a weird argument to me, that they're achieving the best results. They could achieve even better results by choosing linear splines, but they don't. Like, why don't they choose linear splines for theirs to get the best neural scaling?
Well, I think, would this not be?
It's more of a question. I don't think we need to figure out an answer for it, but it's just, it's like, I think that probably if they used splines of order 1, this would the networks wouldn't be able to because that's only linear functions, wouldn't be able to learn a lot of different functions that they have in experiments. So they're using cubic splines instead. But yeah, it seems like there's something counterintuitive here.
Yeah,
I think it might be something to do with the idea of like that if you have like the order of the spline is lower, even though you have them like combined with well, no, actually, yeah, you're right. Like it will be a less complex function that can be represented, which means, yeah. So I think I'm not sure why they chose K. They didn't really justify like K being 3. They didn't really justify that very well. But yeah, they go through some of these results showing that as they go, as they train the network, like this one is the CAN that is like has the shape of 251. An MLP, rather no, sorry, this is still the CAN. So yeah, it will keep decreasing, and at some point, I guess the interesting bit, the important thing to mention here is that every steps in the training process, they increase the grid size. So they make the network progressively and more fine-grained. They also talk about this interpolation threshold. So this is where they find, like, this is where the number of parameters that are trainable within the network starts to match the number of data points that they use to train. And that's where they find that the test loss kind of stops decreasing. So this is where they find, like, it should be a good point to stop training these networks.
And those, can we go back to those curves for a second? One thing that I thought was interesting is like this, the way that the training loss shoots up.
Yeah.
So like the initial training loss at the end of training, and then it has this like weird noisy curve and goes down again. I was wondering what that is.
Well, they say that they did mention about this. Staircase loss curves, yeah. Yeah, so the conjecture that the optimal test loss is achieved. I search for like training. There was something
Yeah, they just kind of wave it off as saying at 1,000 points we enter a bad loss landscape.
Yeah,
They don't say anything
Yeah.
more about it.
Thanks.
Yeah, I'm not sure.
Sorry, got back to the K and scaling alpha. So there's a trade-off between I think the bit about the approximating the function with this, the higher K means a better approximation, a lower uncertainty, and a lower K means a wider uncertainty. I think that's what they're kind of getting at with that bit before they get into the scaling.
Actually, yeah, that makes sense. So basically, if K was smaller, you would be able to you learn the function faster, but probably have worse, like higher variance with respect to error.
Yes,
but
I think it's not something that you can build on, unlike the grid points. So you could start off with a low grid point, but a high K. You can't and increase the fineness of the scale but you can't do it with the order of spline. Sorry, jumping in there. Sorry.
No, that's good. Thank you.
Then they talk about how they perform this grid extension, and I believe it's a like they do it independently for all of the splines in the CAN, and they initialize the parameters for like these more fine-grained B-splines from the coarse-grained B-splines by trying to minimize the distance between these two functions over some distribution of x. They use, I think, least squares to do that. I'm conscious of time, so I'm just going to kind of gloss over some of the other bits. Yeah, so this is what we talked about, this fine graining over time, over the training process. They talk about the fact that the test loss sort of stops decreasing at this interpolation threshold. They also find that the small cans, they generalize better. And they kind of point out that there's some subtlety of choosing can architectures and how to choose them. They say they also propose later on how you can auto-discover such architectures using some regularization and pruning.
One quick question: the toy examples were all noise-free, right?
I believe so. Yes.
Yeah. I don't know whether these are good toy examples. If these splines are pretty good at doing this exactly, whether that necessarily generalizes well to something that works in the wild. Not quite convinced yet.
Yeah,
well, I think the big thing is that the function itself is multivariate. So they're showing how to use like univariate splines to approximate a multivariate function.
Yeah.
But I agree with the point of, so I go back and forth because like from a proof of concept that this behavior, like about all the behavior that they're showing, this is a good paper. From the perspective of showing that this generalizes well to like more practical settings, I don't think they've really addressed that problem.
Yeah. Yeah, they talk about these external, internal degrees of freedom, which I mentioned before. Yeah, and then one way of like they talk about like how they don't know, or you should not be able to know a priori how this shape of this CAN network should look like, which means one way to approach this, which is what they're proposing, is to start from a large CAN network and then train it with some sparsity regularization, followed by pruning. And they do that by like using L1 regularization in the form of a L1 norm on the activation functions. So as in normal like MLP regularization, but instead apply it to the activation functions because there is no linear weights within these CAN layers. They also add some entropy factor to this to finally arrive at like this updated loss, and that allows them to kind of sparsify the network as it's being trained. So yeah, this is the process. They start with a larger CAN, and they train with specification, and then they apply this pruning. I think, yeah, I can skip over that. Yeah, so the pruning will be just like removing any unimportant neurons, and they define the importance by like these two scores. So incoming and outgoing scores. They talk about this idea of symbolification, which means that as you train these networks, you can then manually assign specific symbols, so like specific functions that are identified within these networks. So part of this whole paper is to improve interpretability of neural networks. So one way to do that is to like visualize them, and actually a lot of the work that they're saying that this will be useful for is identifying or like simplifying or identifying functions within data, or like functions that can represent data sets, which can then be symbolified into like equations. So that's an interesting way of approaching this as well, which is yeah, you can affix ones if you like visually inspect the network. You can fix specific functions to specific activation functions. So it can replace, for example, some of these functions like a cosine or logarithmic function. They talk about this in the context of how humans can interact with these scans. So step one would be to train with sparsification and prune the network. You would then assign these symbolic functions. They also have this function called suggest symbolic, which can analyze the function itself, this activation function, and give you a suggestion as to what symbol to assign to it. Then you further train, but only on the affine parameters.
Over here, I'm not sure if I was correct in this interpretation, but I got the impression that the interpretability that they are talking about is based on being able to basically find all like a symbolic equation for the function that's being learned. Is that true?
Yes. So one way, I guess one application of this, like this whole paper is sort of targeted towards ML for physics and ML for math, and they kind of talk about this whole paper as or this idea as a way to help physicists and mathematicians to discover or rediscover equations in different ways. So definitely like this visualization part and the assignment of symbols to specific activation functions is a big thing of this whole process. And then can output this symbolic formula. They go into a little bit of discussion as to why not symbolic regression. And I found this one kind of interesting, where they want to display these CAN networks as sort of the brain to users, and then the users could perform surgery on that brain. I'm not sure how to interpret that, but I think section 3 is like the evaluation or beginning of the evaluation, and they talk about like this toy data set where they have different functions, like the Bessel function, the some sort of like composite function here, multiplication, a function with really high dimensionality on the input, and then some other functions that are like have four input dimensions. So they train these, increase the grid points by like steps of 200. Also train MLPs with different depths and widths. And they compare those two. So these are the results. So for these toy examples, yes, like CANs with quite shallow depths can really sort of approach the theoretical like Pareto frontier of test loss versus number of parameters. So while like MLPs plateau quite quickly. So that's one of the results. So for these, they know the CAN layer, so that it's manually constructed of like, or not the layer, but the CAN network is manually constructed, and they like cherry picked specific CAN shapes for specific problems. However, like for other approaches, like we don't necessarily know what's the best CAN shape for a specific function. So one way to do this would be to how did they do this? Yes, so essentially to start with a very large CAN, and then they sparsify and prune it to obtain a smaller one until they reach a good test loss. They find that the shapes of these auto-discovered CANs are surprisingly compact for these special functions. And they still they still perform quite well. I think the interesting bit was about the Feynman datasets. So the Feynman dataset contains like many physics equations, and they skip over any of the univariate problems because they're quite trivial for cans, because they can be simplified to a 1D spline approximation. And so they focus on like 2 and more input functions, or where the dimensionality is 2 or more. They construct this data set by randomly drawing inputs and outputs of these, by randomly drawing inputs of these for these functions, running these functions, and then that gives them the sort of X and Y of the supervised training. And for the evaluation, they compare 4 different types of neural networks. So ones that were constructed by humans. So given this sort of formula for an equation, a human would sit down and try and figure out the best can shape for that specific equation, and write it in this Kolmogorov-Arnold representation. They had ones that were not pruned, so just a very a fixed shape of a can. One that was pruned and specified and pruned, and then they did MLPs with fixed width. So what they found is that, like for these for the Feynman data sets, the results are quite mixed. So sometimes MLPs are better than cans, sometimes cans are better than MLPs. And their explanation for this is that these data sets are too simple for cans to make further improvements, in a sense that the variable dependence between these functions is usually smooth or monotonic, which is kind of different from the special functions that they had in the first part of the evaluation. They also found, that these auto-discovered cans are smaller than the human-constructed ones. They talk about solving partial differential equations. So that's another part, and this is where we get to like these repeatable functions that I'm trying to approximate. I'm really conscious of time, so I think I might stop here. We've sort of got to the evaluation. It's a very long paper. I haven't really approached even the more complex part, like the application type evaluation with like knot theory. It's just not something I'm familiar with at all, so I don't think I can talk about it. It's an interesting paper. There's some like one problem that I've seen identified like online was that it is extremely difficult to parallelize this over a GPU. So for example, like any training that you want to do on these must happen on CPU, because there is a like during the calculation of these B-splines, there's many branching points, and these are very hard for GPUs to parallelize well, because each of those kernels will have some sort of like decision to make. So at the moment, they're not very well suited for large scale training, which is probably why they did a lot of the experiments on really small toy data sets. It'd be nice to see something like MNIST, attempted with this. I think we're out on time, but if we have any questions.
It's not
maybe more of a comment, but I remember there was in the paper somewhere a decision tree of when should you use cans.
Yes, that's a really cool.
I felt they were sort of blowing their own trumpet there a little bit. I think it's way. Probably they are right now. They have a niche use case, right? This exploratory simple function finding is really cool, but I don't see them like scaling up that well without any linear parts anytime soon. I think the hype hasn't helped really.
Yeah, you're right. I think there were, I saw some attempts of like people trying to combine these with transformers and like self-attention layers, but it runs into issues with like both the dimensionality even though they claim that the curse of dimensionality is sort of not applicable to this. But yeah, like the speed of processing, we don't have the right hardware to run this efficiently.
But I think in principle you could take almost any neural network, right, and replace activation layers by this spline interpolation, and we would expect that it should do quite well, right? Because we just add additional parameters that could be trained, and in edge cases where there is a very good smooth functional representation underneath it, it should do very, very well then.
Yeah, I could see that happening. So you mean like having both the weights on the edges in the typical NLP, but also replacing the like array with the B-spline? Is that what you meant?
It should be possible, right? Because it's all back propagatable. I mean, it would still run in the same performance issues as you mentioned before, of the splines being spline training probably being hard to parallelize, but you know, it's having a new activation function of sorts is always nice.
Yeah. No, definitely. Yeah, interesting diagram as to like, if you want fast training, don't do. Yeah. Cool.
I think it's also they did try it on MNIST, but they did not use a pure CAN network, but rather I think linear layers plus CAN, and then that worked. And
was this in the appendices somewhere?
No, there was, I think.
Oh wow, someone did GPT-2 with CANs. That's brave. Yeah. Wow. Okay. Was it like takes a week to do on one epoch? That'd be interesting to see that. Yeah. Thanks for the link. Yeah. Thanks a lot, everyone. We're slightly over time, but yeah. Thanks for coming to the paper club.
Thank you very much. Very interesting.
Thank you all. Have a good weekend. Thanks, Damian.
Thank you, everyone. Cheers.
Thanks. Really interesting paper.